Hey folks, welcome back to the Combo Classroom for another bonus video where today I want to talk about times tables or multiplication tables and a pattern hiding in them related to sort of a double appearance of square numbers. Now, I've already noted in the past in some content I've made about how multiplication tables are secretly underrated that square numbers are hiding on the diagonal of this times table, and that gives square numbers the special trait of being the only numbers that appear here an odd number of times, because all of the others have a sort of mirror or symmetry to them. Like if I look 2 that way, it's the same as looking 2 that way. And I've even noted that next to this diagonal, we have numbers that are exactly 1 apart from the square number. But today, I want to explain why an even deeper pattern related to square numbers occurs here. And that pattern is looking at the diagonal and going diagonal from there, but not just 1 cell away. For example, let's pick the square number 16 and let's look diagonal 2 squares away in either direction. In this case, we get 12, and we're not going to be looking at that result itself, but rather the difference from the square number, because we saw the seed of this pattern just by noting that the single diagonals away from here are exactly 1 apart from the square number. Well, in this case, going 2 away leads to a number that is 4 less than the square number. And that's the same for all of these others. That is 4 smaller than that. That is 4 smaller than that, and etc. And what if we went 3 away? Well, 3 away, we end up with a number that is 9 smaller. And I don't need to write down these results of how much smaller they were. 1, then 4, then 9, then etc., because it's already written here. Those are the square numbers themselves. So why, if we pick any square number here on its spot on a diagonal and look diagonally from there a certain amount, do we always get a number that is exactly a square number less than the square number? Well, when we're looking at square numbers less than another square number, like in this case, if we wanted to see 12 as its result, we're taking a square number, then subtracting 4, another square number, or here going 3 cells over. To get that, we're taking a square number, then subtracting 9, another square number. Well, this, you may remember, can always be factorized in a special way, known as the difference of squares identity, where we can always turn that into x plus a times x minus a, because the x's form an x squared, the a's form a negative a squared, and that a times x cancels out with that negative version of a times x, leaving us just with those 2 squares. So, why does this identity show up on the times table? Well, it's pretty simple if we think about it intuitively. If we take a square number here and we were looking a certain amount purely diagonal from that, we also could have expressed that as going up some number and then sideways some number, or down some number and then sideways some number, as long as our sideways is going away from the diagonal in each point. That results in basically looking at 2 quantities multiplied together, that one of them is a certain amount less than our square number, and another is a certain amount more than our square number. Like, let's compare 25 to 16. Well, 25 is 5 times 5, and to get to 16, I can do 5 minus 3 times 5 plus 3. So, secretly here, we have some number minus another times some number plus that thing, where it was a number by itself to form the diagonal, and these sort of represent our marching over to the diagonal. And we know that this always equals x squared minus a squared. And depending how we view this here, we could either see that as, well, you take a number on the diagonal and compare it to a diagonal away, and the difference is a square number. Or that if we take any of these and we subtract a certain square number from it, well, the root of that square number, the number we would square to get it, in this case, let's say we subtracted 9, which is 3 squared. We could march 3 up and over or down and over, and we will reach a number that is that square number less than that. Whichever direction you view this in, I think it's a pretty beautiful pattern, and I wanted to make sure all of you noticed that and saw some intuition for why it occurs. Like I mentioned, I've already made a pretty long episode, as well as some other various content about times tables, which I'll link in the description, that has some other additional patterns. And I've also made a short that shows a visual proof of this difference of squares identity, like outside of times tables. Why is this the case, and could we prove it visually somehow? That'll also be linked in the description, along with some other information and links. Anyway, thank you for watching. Hope you enjoyed, and I'll catch you in the next one.